Hey all, welcome to ShareTrek. I hope you're enjoying your weekend. Today I'm not going to be talking about genomic companies, yet what I will be talking about has a very strong bearing to genomics. We're going to talk about how life started on Earth, and then we'll link it to a revolutionary new discovery in genomics. I'll also be naming a couple of companies that have already started working in this area. So with that, let's get started. Well, friends, welcome back. On the 26th of April 2022, Nature Communications published an article which says the origins of life on Earth could be traced to ancient meteorites that may have dumped water and nucleobases, among other organic compounds, into a primordial Earth. There are many different theories for what conditions were needed for life to form on Earth. One of the most famous is the primordial soup hypothesis, which suggests that intense ultraviolet radiation and lightning provided the energy for the chemical reactions between compounds such as water, ammonia, and methane to begin. The theory suggests that these reactions then led to the creation of molecules such as DNA and RNA, which subsequently became part of a self-replicating system which would ultimately become life. Experiments have confirmed that this theory might work, with subsequent analysis showing that more than 20 amino acids crucial for life were synthesized by trying to simulate those conditions in a lab. Another theory suggests that alkaline vents on the ocean floors, being rich in compounds needed for the formation of nucleic acids, may have spurred life. It's now theorized that meteorites delivered nucleobases which make up the structure of the RNA and DNA. While guanine and adenine have previously been identified, the discovery of cytosine, uracil, and thymine completes the set of amino acids needed to form a base pair. Once these elements reached Earth, the environmental conditions may have provided a fertile ground for the amino acids to combine, recombine, break apart, until a viable DNA was created to seed life. Japanese and American scientists studied three carbonaceous meteorites which fell in, one fell in Murchison, Australia, another in Lake Murray, USA, and one more in Tagish Lake in Canada. Samples were taken from these meteorites and ground into a very fine powder, allowing the organic components of each of these meteorites to be extracted. All five of the purines and pyrimidines which make up DNA and RNA were detected in the meteorites at concentrations like experiments replicating the conditions of the early universe, which were simulated in the lab. The researchers ruled out that these components were the result of contamination of the meteorites after the meteorites landed on Earth, because the nucleobase concentrations in the meteorites were different from the soil found in the areas they landed. The typical precursor for their biological formations were mostly absent, suggesting the molecules formed in a way unlike those on Earth, and they rode on the meteorite to reach Earth. The next step is to analyze samples of asteroids which may have been similar to the parent bodies of these meteorites, potentially allowing the researchers to confirm their findings. And these meteorites have to be in space so that they are still uncontaminated. NASA's Lucy mission hopes to visit 8 asteroids in the coming decade, including C and D type asteroids, allowing scientists to discover even more about how these bodies contributed to the formation of the solar system. This will enable us to have an uncontaminated sample to be tested to replicate results found from the 3 meteorites that are found on Earth. And last, let us take an example. I want to just transfer my thoughts to you. I come from a computer science background, therefore I'm going to give you a computer example, and then we'll draw a parallel to how life formed on Earth with these precursor chemicals. Let's take the example of a file containing computer code. It will be inert until it is loaded into a programming environment that recognizes it and understands the data and command it contains, so that work can be performed on the data and output can be given. In my opinion, the ancient Earth environment was the operating system. Early Earth was very hot, and volatile compounds and low boiling point liquids would have been automatically evaporated and ejected into space and lost from the Earth atmosphere. When the Earth cooled sufficiently, its Goldilocks positions in the solar system from the sun created ideal conditions for life, neither too hot nor too cold, and just about right. And at that time, some meteorites might have delivered water and other volatile compounds, which can now still stay on the environment of the Earth and be available for chemical reactions. While other meteorites might have dropped off nucleobases, these I would consider equivalent to program file and data. In the cooking pot of ancient Earth, these nucleobases might have combined, broken apart, and recombined in a bubbling kind of swamp kind of environment within the Earth, and gone into various combinations until the first DNA was formed and life was seeded. A precursor could have been a virus, because we do not consider virus to be a life by itself, as they have only got RNA and do not grow or reproduce by themselves. This makes them non-living. However, when a virus enters a living cell of an organism, it obtains energy from the host cell and starts reproducing. There might have been many interplays between viruses and bacteria, which are single-cell organisms. And through the process of mutation and evolution, we have a variety of life on the Earth. And we also have viruses, bacterial viruses called bacteriophages. And these only attack bacteria. Phages are harmless to people, animals, and plants. The CRISPR-Cas9 mechanism is used by bacteria to build a database of viral signatures that it had encountered in the past, so that it can use the CRISPR-Cas9 system to identify the RNA signature of a virus on entry into its cell and decapitate it and deactivate it. And that's the defense mechanism for bacteria. And that's what we found, and we are starting to discover more about it. Now we know that apart from Cas9, we have identified Cas7 to 11, which was identified by MIT, and also we have Cas13 to name a few. Today I would like to introduce CRISPR-Cas3. After reading this article, I put the link in the description. Check out the article, it's very interesting. I gather that CRISPR-Cas9 works as a molecular chisel, rapidly and precisely excising a tiny bit of DNA at the targeted site. Whereas CRISPR-Cas3 employs a different bacterial immune system. The key enzyme in the system, Cas3, acts more like a molecular wood chipper, removing long stretches of DNA more efficiently. Unlike Cas9, when Cas3 binds to its precise DNA target, it begins chewing up one end of the double-stranded DNA in both sides and exposes a single strand, thus deactivating it. This system can potentially shred a phage DNA and render it inactive. Scientists have dubbed CRISPR-Cas3 as Pac-Man because Cas3 binds to its precise DNA target, and then, like Pac-Man, it starts chewing up one strand of the double-stranded DNA in both directions, exposing a single strand. Also, for lay people like us who are interested in genomics from an investment perspective but are not scientists, it's a very, very easy term. We can easily relate to Pac-Man and associate it with the phenomenon that the scientists are trying to describe out here. I think if CRISPR-Cas9 is the handsaw, CRISPR-Cas3 may be a chainsaw in comparison. It's still early days, and scientists are increasingly finding that CRISPR system is versatile and can be customized to create different tools of varying precision. These tools can then be used to analyze, modify, and gather more knowledge on how the DNA system works. Every bit of knowledge gained in the process is going to create new therapies to combat diseases and infections. We already know how CRISPR system is used to create CAR-T therapy, and also we have seen base editing. There are many more innovations to unravel and progressively improve the quality of life of mankind. At the core of it all, we are in an ancient battlefield where organisms fight each other at microscopic and macroscopic level. With every success and defeat, the organisms learn genetic lessons and become more robust to handle the next attack, or become more vicious to overcome defenses. If this trend continues as we develop more and more novel therapies using CRISPR and the Cas systems, pathogens will also possibly evolve and become more difficult to defeat. In our lifetimes, we are surely going to see increasing quality of life due to the CRISPR revolution. The evolutionary race among organisms will continue long after we are gone. I've put links to reference articles and recommend them for a deeper dive and better understanding. So check out the description, and please make sure that you go through it. It will help us with our genomic investment by increasing our knowledge base on the potential possibilities that are ahead of us. And after looking at this particular article and going through it, and also reflecting on the video I did yesterday of Gingko Bioworks. I think Gingko Bioworks is trying to do exactly this. It's trying to find various combination of amino acids, and it's creating a catalog of organisms and how they deal with the environment around them, what is the output they produce, what is the input they break down, and it is creating what is called as a code base. And the foundry is their factory where they can use the blueprint of each of these organisms that they want to replicate, and the foundry can create them in large numbers very efficiently. That's what Gingko Bioworks is doing. I'm also going to show you a tweet here from Jennifer Doudna. I think I saw it earlier this morning. I think it was an early morning tweet. It talks about a new company, and I'm going to show you the website of the company out here. Just please bear with me for a second. Here is the website for the company, and as you can see, it's also more or less similar to Gingko Bioworks. So now Gingko Bioworks is going to have some competition. So I welcome all of these things, but my only word of caution for investors would be that with the code base that Gingko Bioworks is generating, or something equivalent to the code base, the intellectual property or the database of knowledge that the new companies are going to create, it exposes us to a big risk as humanity, because DNA is the source code of life, and if there's a rogue DNA out there, it could affect all of us and all the living things on the planet. So a lot of malicious actors are there who would like to get their hands on these kind of things. So that's the only point where I'm still leery about it. I think these companies should have really good background checking of all their employees who have access to this kind of information and technology. And also governments should start monitoring this, just like they monitor nuclear energy and nuclear fissile material. So this has to be handled very carefully with a lot of controls in place so that it's not abused. So with that caveat, I think I would like to give thanks to a friend of the channel, Max. Max has always been giving me very interesting articles on which to make videos. This article again came from Max, and he gave it to me almost at the beginning of the week. It took me quite a while to do all the research and understand and bring together all elements from different articles from different places into this coherent video where I'm trying to put everything together and come up with a conclusion. I think very interesting times lies ahead for us. We are not only talking about gene therapies, but we are also looking at potentially creating new organisms that can break down plastics and help us to get rid of the plastic contamination that we have done to the earth from the plastic revolution, where we started making everything from plastic. Now that we are wiser and we have reduced our use of plastic, we still need to dispose of all the non-decomposable plastic that lie ahead. So we could potentially visualize an organism being created and held in a controlled environment in a facility where we just dump the plastics, and the organism decomposes that, and we just start reusing the decomposed components to build other new materials and use them. This way we'll have a much more sustainable earth. And also this can help create organisms which can change greenhouse gases into inert gases, or maybe more friendly gases. So all those possibilities come up with this kind of understanding of how amino acids can be combined and new organisms can be created. So that, my friends, brings me to an end of this video. It's a bit long, but this is the kind of video I really enjoy doing, because it pulls together information from different places and comes up with a thesis and helps us to visualize what genomics is going to hold in store for us. So friends, if you like this video, please press a like out there. And if you're not yet subscribed, please subscribe and help us grow this channel. We are at, I think, 658. We want to touch 1,000 in the next 30 days. That's an ambitious target, but I think, guys, you can help me out. And if any of your friends are interested in genomics investments or genomics in general, please send them a link to our channel and encourage them to have a look. And if you're interested in any particular genomic topics, just like Max sent this article to me, send me suggestions if it is good and if it's within my intellectual capability to pull together a coherent and interesting video, which is plausible. I'll definitely make an attempt to do that. With that, my friends, I would like to bid bye to you. Have a great day. Enjoy your weekend. Bye for now.